This is the second of a series of two talks by Maulik and Shen. Junliang is going to tell us about the Moduli of Higgs bundle and the P-equal-W conjecture.
Okay, so I hope this works well. Thanks for coming back. So this is the second part, which is a continuation of discussions for, I should be closer to this. For model of Higgs bundles and with a focus on the P equals W conjecture. So let's first recall where we were yesterday. So we always consider C to be a curve, a Riemann surface, fix two integers, rank and the degree, and we assume that they are co-prime. And the Abelian-Hodge theory gives us a correspondence between two very different modular spaces who are of different flavors, which I label them with the topological one and the algebraic geometry one. So topological one is the character variety which only relies on the surface group, the pi1. It parameterizes pi1 representations roughly. And of course, by the definition, does not depend on even the complex structure of the Riemann surface you start with. And which I denoted by M car, character variety. And the other one is the model of stable Higgs bundles, which obviously in this algebraic geometric object, because it parameterizes stable Higgs bundles on the Riemann surface of rank R at a degree D, which is denoted by MH. The H stands for Higgs. So we discussed at the end of yesterday's lecture that M car, the character variety, actually has a very interesting weight filtration. So if to get some feeling about how interesting or how complicated it is, we showed in one of the slides of yesterday, there's a HRV formula, the conjectural formula by Hausel, Rodriguez, Villegas, who basically tells you the complexity of the weight filtration for the character variety. So it's described by combinatorial data in terms of certain actually Magdalena polynomials. So just one side remark is that because we know by the assumption that R and D is co-prime, we know that M car is smooth. So, but it's a smooth but not non-proper variety. So we know that the weight filtration, the non-trivial part of the weight filtration for HK, the kth cohomology actually goes from K to 2K. So every class in HK has weight either from like K to 2K. You cannot have classes with smaller weights. So this is a consequence of the smoothness of the character variety. So on the other hand, if you look at the Hitchin model, the model of Higgs bundles, then because of the C star action, it's not very hard to show that actually MH has a trivial weight filtration. In other words, although this is not a proper or compact variety, the Hodge structure is the mixed Hodge structure is actually pure. So every class in HK has weight K. Okay, so here the more complicated or more interesting object to look at is the weight filtration for the character variety associated with the surface group. Okay, but let's now move to the Higgs bundle side. So we mentioned yesterday this admits a Lagrangian fibration, which is the famous Hitchin fibration or Hitchin map. And using that, we actually can filter the cohomology by so-called perverse filtration. So I actually emphasize here the indices here. You see that the perverse filtration by definition, the range, you see that actually goes from 0 to K for HK. So you see that if you look at the character variety, the small weights will not appear because of the smoothness, but here it's not so obvious actually that the small perversity classes will not show up. So this is probably the first place where you see the non-triviality of this correspondence, this dictionary. So when you translate information from one to the other side. So here I'm giving, this is the definition I gave you for the perverse filtration, which is actually in this talk, I will give 3 definitions of perverse filtrations in different settings, and they are useful for different purposes. So this is a definition 1, which essentially is exactly a theorem of Mark and Luca di Cataldo-Migliorini. So if you want to filter the cohomology by looking at what's the kth piece of the perverse filtration, you consider a general affine subspace of the Hitchin base, and then you consider the classes which vanish after restricting over that. So when you restrict your classes over different affine spaces, subspaces of different sizes, you filter the global cohomology, and this filtration obviously govern the information of the topology of the Hitchin map. And then the Peebles W conjecture is that if you look at the mixed Hodge structure, the weight filtration on the character variety via this highly transcendental map of the non-abelian Hodge theory, then on the other side, the information is given by the topology of the Hitchin map, which is, in other words, the W2K, the 2K piece of the weight filtration is matched with the case piece of the perverse filtration. By looking at this statement, actually, the first question you might ask is, what about the weight filtration in odd degrees? And we will see actually in a few minutes that the weight filtration for character variety only jump at even degrees. So in other words, W2K minus 1 will be the same as W2K. So there's no, nothing interesting happens at odd degree. So, okay, so this is the recap of something we discussed yesterday. Let me start with two examples. The first one is trivial, and the second one is already interesting. So the first example, we consider the case where the rank is 1. So we have discussed yesterday, in this case, the character variety is just a product of 2G copies of C star. This is an affine variety. And it's not hard to calculate the weight filtration there because, if you consider C star, we have discussed yesterday that the only non-trivial class H1 there is of weight 2. So then, the Kunis decomposition is compatible with mixed Hodge structure. So in particular, that only the 2K, the highest weight piece, will show up here, will survive here. There's no lower pieces for the weight filtration. So everything's reduced to that calculation for H1 of C star. Okay, but we can also do the calculation for the other side. So the Hitchin map in the other side is basically the projection of the Jacobian variety of this curve, which parameterizes line bundles, cross C to the power of G, which parameterizes Higgs fields, which are, holomorphic differentials. So holomorphic symplectically, you can think of the right-hand side as the total space of the cotangent bundle of the Jacobian variety of the curve. So in this case, the Hitchin map, which is the affinization map, is just the projection to the second factor, which is CG. So in this case, we can also see that the shape of the perverse filtration is trivial. So the top part will contribute and the lower parts are 0. This actually is obvious from the definition 1, that the restriction to any linear subspace, affine subspace as isomorphism among cohomology, because this is a trivial fibration, unless the space you choose is empty. So this means that there's only one place things jump, which is exactly the PK part. So this is a trivial example because both sides are too simple. So that the mixed Hodge structure for product of C star is very simple, and also the topology of the Hitchin map, which is a trivial fibration, so it's also simple. But now let's move to a non-trivial example, which we also discussed briefly yesterday, which in this case, something non-trivial already happened. So the left-hand side is the character variety I explained yesterday, which is a affine cubic surface. So you have S3 is a cubic, surface, a projective cubic surface from which you remove a triangle, and that's an affine variety whose corresponding Hitchin map is an isotrivial fibration given by you take the E cross C, which is the example 0 in the case of genus 1, and you quotient out by the involution, which will create 4 singularities and take the quadrant resolution of it. So the picture is given here that it's isotrivial fibration away from the central fiber, and that the central fiber has 5 components. You have 1 thickened P1 and 4 exceptional divisors. So then, okay, this is actually the first places where you see something non-trivial happens for the perverse filtration. So if you look at the cohomology, there's only one. So yeah, the cohomology of this space is very easy to analyze. You have one class in H0, which is this fundamental class, and there's no H1, and there are 5 classes in H2. So this elliptic surface has 5 classes. Who are they? So there's one relative, so this is proper map to the affine line. So there is a relative ample class, and also 4 exceptional divisors given by these 4 curves in the central fiber. So these are the 5 classes. But now if you look at the locations of the perverse filtration, you see there is a shift. These 5 classes are not of the same status. Yeah, but this is actually easy from the definition. Why? Because so the only thing you can non-trivial thing you can test is you see whether these classes vanish after restricting to a general fiber, right? Because the base is one-dimensional, so the only non-trivial thing you can test is you see whether it vanishes after restricting to a general fiber. And you know that this does not happen for the relative ample class because it's everywhere. But for this exceptional divisor, because they are rigid, they're not movable, so so they vanish, so you will have a shift. These 4 classes, their trivial bound for the perverse filtration is 2. But because of the thing I said, their real perversity is actually 1. So this is the shape of the perverse filtration. I mean, I'm writing down the associate graded. So there's 1 class, which is a fundamental class, which is of perversity 0, 4 classes, which are the exceptional divisors of perversity 1, and 1 relative ample class of perversity 2. If you still remember the counting function over finite fields for the cubic affine surface, you realize this 1, 4, 1 exactly are the coefficients for counting points over finite fields over F cubed. So oh yeah, then. Sorry, oh yeah, so here I'm using a different notation. So the K here is the perverse degree, and the J is the cohomological degree. And when this class happens here, it depends on the restriction to a fine subspace of dimension, which is dependent on both J and K, the cohomological degree and perverse degree. So in other words, if you fix J, then the larger K you consider, you are considering what classes vanish at a smaller fine subspace. Yeah, sorry, I changed. The K upstairs is for cohomological degree, but in this notation, I'm using the perverse degree. I hope it's a little confusing. Sorry for that. Yeah, thanks. Does that answer your question? Okay, so no, complex. Here, everything I'm writing down is complex. Yeah, there might be a typo in copying the index, but so the rough idea is that you look at when the classes vanish after restricting over a general linear space, and when it vanishes, it tells you which piece of the perverse filtration it lies in. Affine, yes.
Like, is there any interpretation that the S3 as a affine goes to like that triangle? Some goes to like that.
I think this description is okay. I mean, you have the compactification as S3, and you remove the compactification. The S3 is a projective cubic hypersurface, and remove a triangle. Yeah, this compactification is okay, I think.
Yeah, it didn't look like that.
Yeah, I think so. Okay, so actually, here you see that the subtlety comes from this shift from the cohomological degree 2 to the perversity 1, and this phenomenon, actually, this is exactly the difficulty in proving the conjecture that there is a gap between the obvious bond, the perversity bond, and the expected perversity bond predicted by the wave theory. And so the key point is to see this. Okay, so I already gave you the first definition due to Mark and Luca for the perverse filtration when the base is an affine space. Now I'm justifying the name perverse filtration, why that natural definition is perverse. This is actually, this is the real definition, which I call definition 2. So for any projective morphism, which I assume that every fiber has dimension D, so everything I'm talking about is complex in complex setting. So complex dimension D. So for convenience, let's assume X, Y are smooth. And the decompensation theorem of Billingson, Bernstein Zelin and Garber tells us that if you push forward the constant sheaf upstairs, so it splits into some building blocks downstairs in the derived category of constructible sheaves, which are semi-simple perverse sheaves. So I will not define what is a semi-simple perverse sheaves, but you can think of this as a generalization of the degeneracy of the Leray spectral sequence for smooth maps. So, but this decomposition is not canonical. This is not a canonical decomposition, but there is a way to make things the canonical on cohomology, which is to consider exactly the perverse filtration. So the pk of the total cohomology is nothing, but you collect the contribution from the first k plus 1 objects of this pi. So because if you consider hypercohomology of the left-hand side, this recovers you the total cohomology of upstairs, x. And then the right-hand side tells you that if you take the truncation at the case place, it filters the total cohomology, and this is exactly the perverse filtration. Because this contribution is actually can be written in terms of the truncation function, 6 operations. So the perverse filtration is canonical, although the decomposition theorem of the BBDG is not. So in other words, the perverse filtration is the cohomological shadow of the sheaf theoretic decomposition theorem. So this is the information you see on global cohomology for the decomposition theorem. Okay, let's come back to, so this is a complete general definition which works for any projective, even actually proper morphism. You don't need to assume that Y is affine, for example, works generally. Let's come back to the P equals W phenomenon. So I have already mentioned some consequences, and maybe let me continue to discuss why interesting. So the main reason is actually this is a bridge connecting to different structures. And so if you start with something trivial on the one side and you translate to the other side, you'll get highly non-trivial consequences sometimes. And I will do several examples, starting with the one actually is the motivation for the formulation of this conjecture, which I actually learned from Mark. So, okay, so for many people, actually, the first place where we see the perverse filtration is the relative hard lattice. So if you're given a morphism, say in this case, it's the Hitchin map, and if we pick a relative ample class, so this is the H2 class on the total space, which acts via the cut product on the total cohomology. And if the base is a point, then you know there is a hard lattice, which you know the cupping product with this class induces symmetry for cohomology. And the natural question is, what happens if you consider relative setting? It's a relative, well, it's a proper or projective map. So even to formulate this for the global cohomology, you have to use the perverse filtration. This might be the first place where, for many people, perverse filtration first show up. So this is the statement of the relative hard lattice. So taking the cut product with a relative ample class, the case time, induces an isomorphism not for the global cohomology, but for the associated graded for the global cohomology with respect to this P filtration. So this is the D minus K piece is isomorphic via this cut product with the D plus K P, where the D is of course the relative dimension, which is also the dimension of the base. Okay, so if you have a bridge like P equals W, you can just move everything to the character variety side. You ask what's the meaning of that? Oh, it's written in this red line. This means that the weight filtration associated graded with respect to the weight filtration of the mixed Hodge structure satisfy a lattice type symmetry, where it is induced by some class of weight 4 in H2. So actually, this phenomenon is called a curious hard lattice, which is conjectured first by Hausel-Rodriguez, Villegas, by their calculations of the weight polynomials, and this was actually proven by Antomalet in 2018, using a cell decomposition for these character varieties associated with surface groups. So this was actually this conjecture, curious hard lattice conjecture, was proposed actually based on the weight calculation, as I mentioned, and a P equals W conjecture was the formulation of the P equals W was inspired by that. So it's to explain this interesting symmetry, because every time when you see some Laffish symmetry in either Kähler geometry or algebraic geometry, sometimes you need some compact direction at least. But for the affine, these character varieties, they are affine. So it's totally open. There's no any direction where it is proper. And the idea for, I think, the Cataldo-Hausel-Migliorini is that this hidden properties should be seen after passing through the non-abelian Hodge theory to move to the Hitchin side, so that you have a very natural candidate, which is the Hitchin map. But if really the relative Harder Laffish explains this phenomenon discovered by HRV, then you must have the match of these two filtration, which is the original, I think, the origin of this conjecture. Okay, this is the first thing where structures on both sides look quite differently. And there is a second one, actually. So we learned from actually mixed Hodge theory that the weight filtration is always multiplicative. So the weight filtration is always compatible with cut product. If you start with the class in weight K, and you take the cut product with the class in weight K prime, it will be landed in the class of weight K plus K prime. So the weight filtration is multiplicative. And if you have this P equals W match, then you know that the perverse filtration should also be multiplicative. But this is actually mysterious, because in general, this is wrong. So it is easiest example you consider is you take a trivial fibration, the family of P2. So this is a trivial fibration, and of course the perverse filtration, which is the same as the Lorentz filtration, is multiplicative. But now you just blow up a point. So now you get a flat family with only one singular fiber with two pieces. This is exceptional divisor, which I denoted by E. And other fibers are just P2. And for this geometry, actually, you see immediately that the perverse filtration fails to be multiplicative. Because the E, it's actually an interesting exercise to test this using the first definition. So the E lies in P1 of H2, and E squared, you can show that it does not lie in P2 of H4. Even more, you can show that the P2 of H4 is actually 0. Yeah, this is the theorem of Mark and Luca. Yes. Yes. Actually, in this example, you can check this statement using both definitions. So yeah, this is interesting exercise. Of course, they are when the bases are fine, like in this case, these two definitions are the same, which is the theorem of Mark and Luca. Yeah, thanks. Okay, so this means that understanding the multiplicativity for the perverse filtration in abelian fibration plays a key role in this entire story. And actually, a good understanding of this has many more applications, and some of them probably will show up in some of the afternoon talks, including mine on Friday, and also Chi-Zhen's in this afternoon. Okay, so these are two quite straightforward translation on both sides, but now let's move to a slightly it's more non-trivial one. With the observation, this observation I learned from the paper by Chuang and Diaconescu Pan, and this concerns the connection between this P equals W phenomenon to enumerative geometry, which concerns counting curves in Calabi-Yau threefolds. So let's briefly recall the setup. So given a Calabi-Yau threefold at a curve class beta, so we have seen several curve counting theories over the week. So for example, the Gromov-Witten theory, which counts stable maps, or Jonathan-Thomas theory, or Pender-Thomas theory, which counts sheaf-like objects. And not surprisingly, they are, well, actually it's quite surprising, but now it's, after many years, it's not that surprising that they are equivalent. They give you the same information. And there's actually a third proposal in physics by Guba, Kuma, and Vafa, and in mathematics, the most updated version is due to Davesh Maulik and Yukinobu Toda in 2016. So the proposal is that we can read off all these Gromov-Witten or Donaldson-Thomas invariants from one modular space, which is the modular space of stable one-dimensional sheaves on this Calabi-Yau threefold. So you fix the support of these sheaves to be the curve class beta, and the Euler characteristic of these sheaves to be 1. So this is the modular space of one-dimensional sheaves on Calabi-Yau threefold. And the Guba-Kummer-Waffa or Maulik-Toda proposal is that so the all genus Gummel-Witten invariants should be read off from by considering just two things. One is the cohomological theory for this modular space. So I'm here writing down, it's a slightly technical thing, which I read is BPS cohomology, but for today's talk, it will be just the singular cohomology. So the cohomology of this modular space together with an extra structure, which is the perverse filtration. So you have a filtered graded vector space, and from which you can read off all the Gummel-Witten or Donaldson-Thomas invariants. So yeah, this definition of M beta X reminds you of the second definition of model of Higgs bundles, because I introduced yesterday that if you consider X to be T star, the total cotangent bundle of the Riemann surface, then the model of Higgs bundles can be described this way. So this suggests that there might be a connection, and here it is. So we start with our curve C, and we can cook up, the easiest way to cook up a Calabi-Yau from the curve is, you just take the total cotangent bundle of it. So you upgrade this to T star C, so this is a Calabi-Yau surface. But now you want to Calabi-Yau threefold, so you just cross a trivial factor, which is C. So this is the easiest way for you to construct a Calabi-Yau threefold from your curve. And we consider the curve class beta to be R times the zero section of this Calabi-Yau threefold. And in this case, so one can show that this Guba-Kummer-Waffa modular space is nothing but just the model of Higgs bundles of rank R, where this degree D is actually, by Riemann-Roch calculations, the degree D is determined by the Euler characteristic, which is 1. So the modular space is basically MH cross C. And if you open the Maulik-Toda proposal, it says that the Guba-Kummer-Waffa invariants, which are read off from the perverse filtration associated with the Hitchin map, should be matched with the Gummel-Witten theory for this local curve. Very fortunately, the Gummel-Witten theory was calculated more than 20 years ago by Jim and Rahul using a TQFT formalism. And this is the right-hand side, this is actually an observation. So there's a closed formula for the Gummel-Witten theory of X. And there's an observation by Trond Diaconescu-Penn, who can rewrite Jim and Rahul's formula using the counting function over the character variety by looking at the closed formula of Hausel-Rodriguez-Villegas. So both sides are closed formulas so both things on the right sides are closed formulas, and you can match them. So in other words, the proposal of connecting Guba-Kummer-Waffa and the Gummel-Witten, in this case, is to show that the dimensions, the certain functions given by the dimension of the perverse filtration should be matched with the counting function of a finite field for character variety. And this is exactly a shadow of People's W. Because if you look at how to get the counting function from the weight polynomial, you plug the same formula on the left-hand side, that's exactly Maulik-Toda proposal. So in other words, so P equals W tells you that the Gummel-Witten and the Guba-Kummer-Waffa correspondence holds for this local Calabi-Yau for any curve class. Yes, Dan? You mean where X is compact? Yeah, this is a very complicated story, and where X is compact, you should not consider the singular cohomology, but BPS cohomology. So you first need to find the orientation data, and Davesh and Yukinobu told you what kind of orientation data you should use, and then then using this orientation data, you can get some perverse sheaf from which you can get this. You plug in this machine and you get these invariants. Yes. So the Jim mentioned that. So the perverse filtration is for the morphism from M beta X to the Chow variety, parameterizes one cycles on X, which is the Hitching map in this case. Okay, so we have discussed the connections, and I hope I convince you that the translation between these two different sides is non-trivial and interesting. Now let's come to the idea of the proofs. So there are, so the proof requires, so the abelian Hodge correspondence is highly transcendental thing, and in order to match two filtrations on both sides which are of algebraic flavor, so ideally you would like to find a third filtration which is preserved by this transcendental operation, which you can use the third filtration to detect this both filtrations on both sides. So, and this third filtration is given by the structure that another structure, which is the tautological classes on this modular spaces. So recall yesterday that using universal bundle, we can define the tautological class CK gamma, where this K means which Chen character you take for this universal bundle, and gamma tells you which class you integrate on the curve side, because you take Chen character, you get classes on the product, and you have to integrate some class on the curve side to get classes only for the modular space. And this class is indexed by K and gamma, and so its cohomological degree, of course, is determined by K and the cohomological degree of gamma. Okay, so now we can define a third filtration using the modular interpretation of this space, so-called Chen filtration. So I filter the modular space. So by Eo's theorem, we know that every class in the cohomology of MH or equivalently M car is given by these tautological classes. So we can define a filtration CK to be the span of the monomials of these tautological classes. So this K, the Chen index here, the only thing I put here is that these Chen classes, we bound the total Chen grading of the classes on the right-hand side. So this seems to be a very strange thing to look at, because these classes on the right-hand side have different cohomological degrees, but you don't care about the cohomological degree. You only remember which Chen class you take, and then you filter the total cohomology using that. So because the tautological classes are preserved on both sides of the non-abelian Hodge, so this is a filtration which intrinsic structure which actually can talk to both sides of the MH and M car. Okay, so let me, this is a technical slide, but let me go through this quickly. So on the character variety side, so the work of Vivek Shenda in 2014 tells us that, so we can define complete algebraically these tautological classes on the character variety side. And then from which you can show that the Chen filtration, the case piece of the Chen filtration is matched exactly with the weight filtration W2K. So this is, the reason of this is that the reason of this is not hard. So the hardest thing, of course, in Vivek's proof is to set up the question. As long as you set it up, you can calculate, you know that it's clear that the weight will be matched with the Chen, because every tautological class essentially is pulled back from the cohomology of BG, and you know what's the mixed Hodge structure there. You know that the cohomology of PGLR are generated by the Chen classes, and every Chen class, for every Chen class, you know that you satisfy this property. The Chen grading detects the weights, and then using the functoriality of the mixed Hodge structure, you get that the Chen grading is so the Chen filtration is matched with the weight filtration. So okay, so this is now the diagram. So now we want to match P with W. Sorry, there's a typo. It should be 2K. So you want to match P with K. P with W, and you know already that W is matched with C. So these are three completely different structures: the topology of the Hitching map, the mixed Hodge structure of the character variety, and the structure given by the tautological classes. And now the remaining mission is to match the P and the C. So you see that the tautological classes on the model of Higgs bundle interact well with the topology of the Lagrangian vibration. So in other words, it suffices to prove this. And in fact, because we already know the curious hard Laffiers for the character variety, because we know that both filtrations satisfy the same Laffier symmetry. So in order to match them, it suffices actually to show that one is contained in the other. because this is a numerical exercise. If you have two filtrations and one contained in the other, if the containment is strict, it cannot happen that both filtrations satisfy the Lefschetz symmetry. So in other words, the mission is the first. Of course, we have to locate the class, this tautological class, in the right location of the perverse filtration. And moreover, this is already challenging, but this was now essentially in joint work with Mark and Davesh 6 years ago. But since we mentioned that we don't know that perverse filtration is multiplicative, unlike the weight filtration, so it's not enough to treat every individual tautological class. You need to handle the cup product. So in other words, so we need to know that the cup product on the cohomology interact well with the P filtration. In other words, yeah, this is the second line is the thing we really want. So both statements are hard to see from either definition of P. We have two definitions, one using hyperplane section, using the affine subspaces for the base, and the other is to use the decompensation theorem. And actually, either is not easy to see actually this kind of description to see the interaction with the tautological classes. And there's even more, this is actually the essential difficulty. So the higher Chen class you consider, then there are two, so roughly you can imagine that the CK gamma has cohomological degree 2K, because you take the Chen character of some object, the case Chen character of some object. But so the obvious perversity bound is also 2K. But from this prediction, you want this to be just the K. You want to push the perverse degree by a lot. And so in particular, you see that when the rank of the Higgs bundle is higher, there are more Chen classes, you have higher Chen classes, then the question is more difficult. So here are the summary of the ideas of these three proofs. So the three proofs, each proof uses actually extra symmetries of the modular spaces of Higgs bundles. It's very hard to study tautological classes and perverse filtration using the first two definitions. We need more symmetries to connect the CK and the PK. And interestingly, the symmetries used in these three proofs are completely different. Very different flavors. In the work with Davesh Maulik in 2022, we use the global Springer theory in the sense of Ngo and the Zhiwei Yun, where we view this Hitchin modular space as a global analog of Lie algebra, from which actually we can reduce this difficulty. Like this difficulty happens when K is very large. We can reduce this to K is equal to 1, okay, by splitting the vector bundle to line bundles or modifying the modular spaces using Springer theory. And the second proof by Hausel-Migliorini, Minetz, Schiffman, it uses a very different structure, actually has many connections to representation theory and the Donaldson-Thomas theory, which is called cohomological Hall algebra. So they show that the cohomology of MH underlies the action of coha, from which you get rid of the filtrations Chen and perverse. So the third proof, which I will discuss in more details, uses actually a duality of abelian vibrations. The more details will be explained. Okay, so now let's go to the details of the proof. So in fact, we instead of proving things for cohomology, we actually proved a refined version. So sometimes in mathematics, it's a fun phenomenon that you enhance the statement you want to prove, you make it stronger, and then sometimes the statement is easier to prove. And this story is probably one of the cases there, because when you enhance the statement, sometimes you get more structures. So the original question concerns perverse filtration for the cohomology, which lies in the world of Q vector spaces. But since you know that the perverse filtration has origin in the decompensation theorem, we can first upgrade things to sheaf theoretic level by considering the decompensation theorem and the perverse truncation functor. So this already happens on the bounded derived category of constructible sheaves. This is a much more complicated category than Q vector spaces. But it carries more structures. For example, in the last 2 decades, there are a lot of progress in the study of the decompensation theorem associated with the Hitchin vibration. For example, I think Maulik's talk earlier, than some aspects of this was discussed. Actually, we go down, we keep going down. So we can further generalize or enhance this by considering algebraic cycles on the relative product. In other words, we do a motivic lifting for the story we start with. Well, I'll explain what's the meaning of that. So what's the meaning of the lifting perverse filtrations to algebraic cycles? So the general philosophy is given by this wide open deep conjecture by Kodi Hanamura, which holds in complete generality, but which is expected to hold in complete generality, but it's wide open. So it says for any proper morphism with fibers of dimension D, and let's assume X is smooth, then there exists a decomposition of the relative diagonal into 2D plus 1 algebraic cycles in this rational Chow group. And this decomposition is into orthogonal projectors in the sense that if you consider these algebraic cycles pi I on the right-hand side, if you do the composition of them in the sense of correspondences, then if you do pi I with pi I, you get pi itself, meaning that this is a projector. But if you do pi I with pi j, where j is not equal to I, you get 0, meaning that they are orthogonal. Moreover, this decomposition of the relative diagonal controls completely the BBDG decomposition theorem. So more precisely, for every algebraic cycle in the relative Chow group, you can think of this as relative correspondence, cohomological correspondence, which acts on the push-forward complex. And then if you make the diagonal to act on it, you get nothing but ID. You don't change anything, but every pi I on the right-hand side will single you out the semi-simple perverse sheaf pi. So in other words, everything you can read off from the decomposition theorem should be detected by these algebraic cycles if they exist. But of course, if you really want to use this philosophy to solve your problem, one of the biggest challenges is, of course, that this is a conjecture, and unfortunately, it's a theorem for the Hitchin fibration. So but this is part of the conjecture that there exists one decomposition which specializes to a decomposition theorem. Sorry? Well, the decomposition theorem is not canonical, so there's no right one. So yeah, both statements are about existence. So there exists a decomposition of relative diagonal which splits to a decomposition in the sense of BBDG. But yeah, this is a very good point because all the things we essentially cares about concerns actually P and the perverse filtration and the truncation functor. And these are governed by, if you have these projectives, these are governed by just collecting the first K plus 1 cycles. Yeah, every time you have, concerning Yale's question, every time you have such a decomposition, you get an isomorphism of the BBDG decomposition, but there's no canonical one already. So, okay, so the Kodi-Hanamura conjecture holds for the Hitchin map, and moreover, these projectors admits concrete formulas. So these projectors are essentially given by the Fourier-Mukai duality in the sense of Arinkin, which I will introduce in a minute. So by this theorem, then for every question, so if you have a question concerning the decomposition theorem or concerning the perverse filtration, you can trade this by intersection theory. So I just do the example. So, how to show for a class gamma to be lying in PK? Well, you consider the corresponding projector P less or equal to K, which is the collection of pi 0 to pi K. And the Q K plus 1 is the complement of it. So you know that you not only have this filtration part, this P less or equal to K, but also you know that it's a complement. So in order to test whether gamma lies in PK, it suffices to use the complement. So to show that you use the QK plus 1 to act on gamma, whether it's 0. So in other words, this trait the property of showing some class lying certain piece of a perverse filtration by verifying a relation, a tautological relation. And in particular, this is a very general idea. And in practice, actually, both the properties concerning the interaction between a Chen and a P can be verified this way. So at first glance, it's not so convinced because this kind of relation can still be very complicated depending on the complexity of the classes. But the last slide, I will tell you how actually this can be done. So all these tautological relations will be governed by one geometric fact about this abelian fibration, which is the delta regularity. I'll go there. Okay, so in the next a few minutes, I will discuss. So because in this theorem, I said it's this decomposition is given by Fourier-Mukai kernel, and so why this is the case. So I will show in the next slide immediately that actually Fourier-Mukai transform for a derived category provides you a perfect tool of decomposing the diagonal. To analyze this story, let me start with just do a toy example, which was the story 40 years ago by Bouville and Denninger-Moore for abelian schemes. So we consider abelian scheme over a smooth base. In this case, we want to find what are the projectors, what are the pi I in this particular simple cases where there are no singular fibers. So the idea of Bouville and Denninger-Moore is that in order to solve the problem for pi, which is the abelian fibration, you have to introduce this dual. So we consider the dual abelian scheme, relative Picard, from which Mukai told us that there is a Poincare lie bundle inducing a derived equivalence of the derived categories. And once you have a K-theory on a product, you can take the Chen character, which gives you algebraic cycles, which are correspondences. So this slide explains why derived equivalence is a perfect tool for decomposing the diagonal because you get it for free. So by having a derived equivalence, this means that you have phi L, but also you have phi L inverse. And if you compose them, you get the identity functor, by which means this is a Fourier-Mukai transform given by the structure sheaf of the relative diagonal. So this is the K-theory identity. So you can descend from K-theory to cycle or cohomology directly, which tells you immediately that you can split the diagonal, which concerns the left-hand side, to 2G plus 1 exactly exact number of algebraic cycles on the right-hand side. So here, because so you have to go from A to A dual and come back. So there are several ways to do it depending on which degree you assign. So this will tell you how to split the relative diagonal into 2G plus 1 projectors. And then what needs to do some work concerning the properties of this Poincare lie bundle to show that they actually form orthogonal projectors. So the upshot is that once you have moved Fourier-Mukai transform, you automatically get a decomposition of diagonal. But of course, you need to do more extra work to show that this actually gives you the right thing. Fk is the degree. So F is the total Chen character, and the Fk is the degree K part. Because the dimension constraint, it tells you that, so if you take the Fk for the first one, then you have to take F inverse 2G minus K for the other one. This splits you the diagonal into 2G plus 1 sides. Okay, how about singular fibers? Since I'm running out of, so how much time I have? 2 minutes. Okay, so let's go there quickly. So the observation from Springer theory, from using some idea in representation theory, we can show that if we can handle the projectors for integral Hitching fibers, then the Springer theory can extend them over the entire Hitching base. So, but the caveat here is that if you only know the projectors for the smooth fibers, it's not enough. So if you only know the case for smooth fibers, which things are given by Mukai, the Mukai's lie bundle, it's not enough to tell you what happens for these singular fibers. Okay, so let me go to the ideas quickly. So for the models for the singular fibers for the Hitching fibration actually is the family of compactified Jacobians associated with integral locally planar curves. So over this singular locus, Dima-Arinkin constructed an isomorphism of the bounded derived category extending Mukai's original Fourier-Mukai transform. Arinki's original purpose was to understand the classical limit of the geometric long lines via in terms of the Donaghy-Pente proposal. So for which he needs to construct this extension of the Mukai line bundle to this new kernel, which no longer is a line bundle, but a Kahl-Macaulay sheaf. This is a very complicated object because you more or less you know its existence and that's it. So so the construction of this P is to use the Hyman's isospectral Hilbert scheme, and this is a very complicated object, but the short version of the upshot is that we can use this kernel to mimic what Beauville and Denninger-Moore did for abelian schemes without any singular fibers, and which gets you a third characterization of the perverse filtration. So okay, so this is the last slide. Let me conclude the talks by two remarks. One is technical and the other is more conceptual. So the technical remark is that, okay, so in order to make everything work, we'll have to handle tautological relations I mentioned earlier. And this seems to be a very difficult task. And how to do this kind of thing in general? Well, so the difficulty is that we do not know too much about this Arinkin sheaf, except, as I said, except its existence. But ultimately, so we reduce all the properties we need to a single geometric property, which is that this abelian fibration we consider is delta regular. So this is a concept I think introduced by Ngo in his fundamental lemma paper for him to study the decompensation theorem. And for nowadays, by much work in the last decade, people thought this is actually a fairly general setup for studying Lagrangian fibrations. And the delta regularity is exactly the geometric input which makes all these tautological relations happen. So if you're interested in more details, we can talk afterwards. So last conceptual remark from which I will conclude the talk, which this is actually the more down-to-earth version of the third definition of the perverse filtration. So since we have mentioned that we use the Fourier transform, and this is a notion algebraic geometers borrow from analysis, and if it's your first time to see this, you might be wondering why it works, why it's helpful, and why we are interested in doing Fourier transforming algebraic geometry. So in this story here is this line is the answer. So the case piece of the perverse filtration are those classes alpha that if you apply the Fourier transform, on the other side, you only need to know that this class has larger cohomological degree. In other words, so the Fourier-Mukai transform, the Fourier transform in this story can trade the much harder perversity to something much easier on the dual side, which is the cohomological degree. So you get trade information from one side to its dual. And this is, I want to conclude the lectures via the third definition of perverse filtration. And this is actually the one we use to verify all the properties. Okay, so let me stop here. Thanks.